Sorry. Good afternoon, everyone. So, you all to the problem solving session 3 for the NPTEL course Fluid and Particle Mechanics. We'll start the session in 2 minutes. I just fixed my laptop. I just okay. So I guess we will start. In the meantime, let others join. Okay. Sorry. I was just in a meeting, so we can start. I think my all right. We'll start now. So, welcome you all for the NPTEL course problem solving session. The course is Fluid and Particle Mechanics, and course code is NOC 25CH49, and we are in week 3. So, the session will run from 3 p.m. to 5 p.m. And actually, regarding the course instructors are Professor Sumesh P. Thampi and Professor Basavaraj M. Gurappa from the Department of Chemical Engineering, IIT Madras. And myself, I'm the TA for this course, and I'm a research scholar from IIT Hyderabad, Chemical Engineering Department. So, as we know, the course is Fluid and Particle Mechanics, and first half of the course is about fluid mechanics, later half of the course is about particle mechanics. So, in today's class, or till now, this is to give you an overview of the course layout. This is not strictly sticking to the course layout, but overall these will be the content which you will be reading throughout the course, and which knowledge you will be possessed at the end of the course. So it is mostly in the fluid mechanics. What are all the concepts you will be learning? It is about introduction to Navier-Stokes equations. Whenever we talk about fluid mechanics, it is entirely about fluid flow solving problems, and that basically involves Navier-Stokes equations and their exact solutions, and Poiseuille flow and Taylor-Couette flow rheology, dimensional analysis, turbulent flows, friction losses, Moody's chart, and boundary layer theory. And when we move on to fluid particles, we will be having introduction to particles, characterization, particulate phenomena, boundary motion, Brownian motion, and phyrosis, motion of particles in a fluid, terminal velocity, particle separation, sedimentation of dilute, concentrated, and flocculated dispersions, packed and fluidized beds, and filtration. So I have a very interesting connection with fluid and particle mechanics, in that my work is on multi-phase flows. Whenever we are talking about multi-phase flows, it involves more than two phases. So the complexity arises in multi-phase fluids, because whenever we are talking about two phases, either with fluid or particles, we will be we can at least understand to some extent what is happening inside the system. But when we are moving beyond two phases, when we are going for the three phase, we will be having a lot of difficulties encountered during the fluid flow phenomena, and that will be a major factor which requires our complete understanding of the things. So I would not take much time in this, but let us move on to books and references. So we have McCabe Smith, Unit Operations of Chemical Engineering. I am sure many of you are aware of this particular book, because as we know that most of the chemical engineers rely on this book for fluid mechanics, and also like some part of heat and mass transfer also we study from that. But mostly fluid mechanics, we will be mostly using this book, apart from white I mean Frank M White's fluid mechanics. And finally we have introduction to particle technology, when we are dealing with particle phenomena, particle mechanics. So references, we have a few books: Coulson and Richardson's Chemical Engineering, John Metcalfe Coulson, John Francis Richardson. So this is another famous book. All these are very famous books in chemical engineering field. And another reference is Fluid Mechanics by Piyush K. Kundu, Elsevier, 2013. And finally, we have Principles of Colloid and Surface Chemistry, Paul Heymans and Rajagopalan, CRC Press 1997. So, lastly, we use the transport phenomena by Bird, Stewart, and Lightfoot. This is another one famous book which we almost would have used in our UG courses during transport phenomena course. And mostly after that, wherever you go, whichever reference you want, you will be using it at some point or the other. So for BTech people, my advice would be to focus more on learning the concepts from the books, so that whenever in future you are reading some concepts, you can always go back and refer to that particular concept from that particular book. And if you take notes from that book, it is very well. So let me not bore you, but week 3, it is just a quick revision of whatever you have seen in the course. So it is a circular partially flow, shear stress distribution, and flow between two concentric cylinders, Taylor-Couette flow, viscosity and momentum transfer, device for measuring fluid viscosity, fluid properties and its behavior. So these are all the things which you would have learned. So coming back, this why are we going for these problem solving sessions? We are doing problem solving sessions in order to help you people in submitting the assignments. So if you have any doubts, you can ask during these sessions. And if apart from this, if you have any doubts in the assignments, please post it in the forum, wherein you will have some that online discussion forum will be there. So if you post it there, I'll answer those questions. And if you have any doubts, you all have the link to these sessions. So again, you can post your doubts there. I'll be happy to take those questions and answer those questions as far as I can make those concepts clear. I'll do it clearly. So now, so this is the first problem for today's session is: for a fully developed laminar flow in a two-dimensional channel of gap 2h, flow between two parallel plates separated by a distance of 2h driven by a pressure gradient, write the flow governing equations. In all equations, y is measured from the top. Y is equal to 0 at the top wall. So what is the I'll tell you first itself. So most of the problems will be similar to the problems which you will be seeing in the assignment. So instead of that, in those problems I would have given you a method rather than focusing on problems and solutions, because it cannot be same to same problem of what is given in the assignments. So for that reason, I'll be giving you the method of how to solve the problems conceptually. So the similar way, if you apply, you will be having the answer to the assignment problems as well. So first, let us read the question clearly. For a fully developed flow, laminar flow in a two-dimensional channel of gap 2h. So flow is between two parallel plates and the distance between these two plates is 2h. That is what is given in the question. And it is driven by a pressure gradient. So we need to be sure that here flow is driven by the pressure gradient, and we are asked to write the flow governing equation. In all the questions, y is measured from the top wall. Y is equal to 0 at the top wall and y is equal to 2h at the bottom wall. So that is why it is given. We in all questions, y is measured from the top wall. Because normally we will be going as from here to top, sorry, and in general we go like this, but in this particular question it is y is equal to 0 here, y is equal to 2h here, and y is equal to h here, sorry, but anyway in between you will have y is equal to h. So what is given in the question? In the question it is given that for a fully developed laminar flow. So the flow is a laminar flow and channel of two-dimensional channel. It is not a three-dimensional problem. Once again. So we can take x and y, and the flow is driven by the pressure gradient. So here it is x, here it is y. But yeah, not this particular direction, y is in this direction, so we can take it as y x, because y is measured from the top wall. Y is equal to 0 at the top wall and y is increasing towards the bottom wall. I mean, that is how the measurement is done in this particular problem. So okay, so what is asked? We are asked to write the flow governing equation. So we will see how to do that. So the takeaway from the question is that it is a fully developed laminar flow and the flow is driven by a pressure gradient. And we have a flow we have to write the flow governing equations. So what is the inference which we can draw from this question? That is the important thing which we need to consider before moving on to answer. So here it is, flow is happening in the x direction and flow is driven by the pressure gradient. So dou p by dou x will be certainly present in the equation, Navier-Stokes equation. And another thing which we will be having is from top to bottom, velocity, v velocity would be 0. But u component velocity, that is x component velocity, u will be a function of y. It will be varying with respect to y, but v component will be 0. Why? Because it is clearly given in the question that it is a fully developed flow. So since the flow is fully developed flow, we are not concerned about that. U is a function of y. U is varying with respect to height, but u is not varying in the x direction. So basically u is varying in the y direction, so it will be like our basic understanding will be flow is between two parallel plates and it is driven by pressure gradient. So what will be the flow velocity at the top and bottom walls? So top and bottom wall, it would be 0. So if you have any answers which you want to say, you can actually put it in the chat window, but you can unmute yourself and say at any point. I might not see the chat window all time, that's why. So coming back, So this is the x direction and this is the y direction. So here what we are seeing, it is a fully developed flow. So and also flow is driven by the pressure gradient. So here we are saying u is a function of y. So most common condition which we will be using is that flow here and flow here will be it will be equal to the wall boundary condition. So if wall is moving, that velocity at that point will be velocity of the wall. Or if wall is stationary, velocity will be 0. So that is the no slip condition which we apply in most of the times. So here it is not given anything with regards to the motion of the wall. So we are just taking constant I mean 0 at the both the walls, and it will be increasing towards the center. So that is the basic understanding which we have from the question. So now we should derive the flow governing equation. So for that, first step is identifying u. U here is a function of y. So u is varying with respect to height across the two plates. So now we'll see the solution. So first, in plane partially flow, the flow velocity u is equal to u as a function of y, and v is 0 because flow is in the x direction and flow has attained the fully developed condition. So that is the reason. Now what we do, we first write the continuity equation. Continuity equation in the two dimension. In the question it is clearly given that it is a two-dimensional problem. So we are writing the continuity equation in the two-dimensional form, and we will be having it as dou u by dou x plus dou v by dou y equal to 0. So this is the continuity equation. Now we need to check whether continuity equation is satisfied or not. So here u is a function of y. So when we take derivative of u with respect to x, what it becomes? Dou u by dou x will be 0. Now we have dou v by dou y. So v is also 0. So continuity equation is satisfied. So the continuity equation is satisfied. Whenever we are talking about any flow condition, it is very much necessary that we should make sure continuity equation is satisfied. What does continuity equation mean? It just means that mass in is equal to mass out when there is no accumulation. When there is accumulation, accordingly it will be like balanced. But it is basically the mass balance. So whenever a system is having any issues with respect to mass balance, it will be very difficult. So that is the thing why we need to make sure the continuity equations are satisfied. So now after making sure the continuity equations are satisfied, what we need to do is, I think joined or something, right? Okay. Anyways. Navier-Stokes equation in the x direction, we should first write the equation. So why in the x direction? Because flow is happening in the x direction and v component velocity is already 0. So we are going with the Navier-Stokes equation in the x direction. So what is the equation? It is rho into u into dou u by dou x plus v into dou u by dou y. Actually all the u and v should be either italicized, or I should be using the overhead arrow to signify that it is a vector, but in this I haven't given. So but yeah, you understand it, right? So don't follow this. So rho into u into dou u by dou x plus v into dou u by dou y equal to minus of dou p by dou x plus mu into dou square u by dou x square plus dou square u by dou y square. Why we are writing only x and y? Because the flow is two-dimensional flow. So we can stop with only x and y components. So now what happens is that u is a function of y. So if u is a function of y, dou u by dou x will be 0. U will be a here u will be 0, I mean not 0, but dou u by dou x will be 0. Here v will be 0, dou u by dou y will not be 0. So basically the left hand side entirely becomes 0. 0 equal to minus of dp by dx. This remains because flow is governed by the pressure gradient, plus mu into dou square u by dou x square plus dou square u by dou y square. So here again this term becomes 0. Why? Because u is a function of y and it is not a function of x. So it becomes 0 when we take derivatives. Because u is not varying in the y direction. In the x direction it is remaining constant. That's why derivative of the constant is 0. Plus dou square u by dou y square. This term remains because u is a function of y. So what are all the terms become 0? The entire left hand side of the equation becomes 0, and we have this, and we have mu into dou square u by dou y square. This particular term vanishes. So this is how the equation remains after the simplification. So now what happens? We can take dp by dx to the other side. dp by dx is equal to mu into dou square u by dou y square. Mu also we can take other side. So okay, why did I arrive at, yeah, so here dp by dx is equal to mu into dou square u by dou y square. So we are taking mu to the other side, so it becomes dou square u by dou y square is equal to 1 by mu dp by dx. And now we need to know what is u. U is a function of dash. So to get that, what we will be doing, we will do u is equal to 1 by mu dp by dx. We will integrate this equation twice. So u is equal to 1 by mu dp by dx. So what happens when we integrate it twice? So it becomes, on first integration it becomes, sorry, I'll write it here, du by dy equal to 1 by mu dp by dx. So now since we are integrating, this will become y plus some constant, let it be c1. So now next what we will do, we will take the second integration again. So it becomes u as a function of y is equal to 1 by mu dp by dx into y square by 2. So this becomes y square by 2 plus c1 into y plus c2. One more constant we will be adding. This is how we get this particular term. So what are all the boundary conditions we will be using? We are given that at y is equal to 0. Here we are assuming no slip condition, and we are assuming that the plates are not moving. So at y equal to 0, we have u of y equal to 0. Why? Because at y equal to 0, what is that? It belongs to the top plate. So what we are saying is that top plate is not moving. So when it is not moving, because of the no slip boundary condition, u also becomes 0. So that is our statement from that. Next thing is, we are applying the boundary condition in the original equation. Why are we doing this step? We are doing it so that we will get what is C1 and C2. So to get C1 and C2, we are applying boundary condition. So when we apply y equal to 0, u also becomes 0. So if we take y 0 and u 0, C2 becomes 0 because y is 0. This particular term becomes 0. U at y equal to 0, u is 0. So LHS becomes 0. Here y also becomes 0. So it is 0. Plus C1 into y. Again y is 0. So this second term also becomes 0. Plus C2. So what are we getting? We are getting C2 as 0. What is the second boundary condition? Can anyone tell? Okay, I'll tell. It is that bottom plate is also not moving. So at y is equal to 2h also u becomes 0. At y is equal to 2h also u becomes 0. So that is the um, thing. Okay. So at y is equal to 2h, that is at the height of bottom plate, because we are considering flow between two parallel plates. So the plate is not moving. So when the plate is not moving, the fluid layer next to the plate is also having the same velocity as the solid. The I mean, at that point, the velocity of fluid is equal to velocity of solid. We call it as no slip boundary condition. So based on that, we are saying that at the top plate u is 0 and at the bottom plate u is 0. So at y equal to 0 u is 0, y is equal to 2h u is 0. U is okay. I mean at y equal to 2h u is equal to 0. So again we are substituting here and we are getting 0 is equal to 1 by mu dp by dx 2h the whole square by 2, that is 4h square by 2 plus c1 of 2h plus 0. Why this is 0? Because c2 we already found it out as 0. Now what is our ultimate aim? We need to find what is c1. So we keep c1 in one side and take all the other terms to the other side, so that it becomes c1 is equal to minus of 1 by mu dp by dx. So 4 and 2 gets cancelled, it remains 2h square, and we will be having 2h square divided by 2h, it will be h. So that is how we get C1. C1 is equal to minus 1 by mu dp by dx into h. So now we are substituting this particular term back in the equation, and we will be getting it as u of y equal to 1 by mu into dp by dx into y square by 2 plus c1y. So c1 we are substituting this particular term. So minus of 1 by mu dp by dx into h into y. So now after that we are taking all the common terms. So it becomes u of y is equal to 1 by 2 mu, 1 by 2 mu we are taking common, and we are taking dp by dx also common, we are taking a minus. So what happens? It becomes 2h. Y also we are taking it out as common, so it becomes 2h. Why? Because we are taking 1 2 common in the denominator, so it becomes 2h minus y. So u of y equal to 1 by 2 mu e into minus of dp by dx into y into 2h minus y. So that is the equation which we will be getting after all the substitutions. So this is the flow governing equation. So now from this what can we say? So when y is equal to 2h, it becomes 0. So that is based on our condition only. When y is equal to 2h, this term becomes 0. 2h minus 2h, so u becomes 0. When y equal to 0, again this term becomes 0. So because y equal to 0 here. So now, so velocity is minimum near the walls. So that is one conclusion. And velocity will be maximum near the center, because near both the walls it will be minimum, whereas near the center it will be having a maximum velocity. So that is the conclusion we draw from this particular problem. So velocity is maximum near the center and velocity is minimum near the walls. So based on this, we can solve all the other problems that can come from this. So that is the solution for this particular problem. So now we will go on to next problem, that is okay, question 9. So question 9 is a problem with a manometer kind of a thing. So what we got here, we are having some mercury. The Hg is mercury here. So, and we have oil flowing in a pipe, and we have connected some manometer with mercury manometer. So the height difference shown by the manometer is h, and this particular distance is 2.5 meter, and the fluid is flowing with a velocity of v, and the fluid is oil, and the diameter of the column is 9 centimeter. So now we will just read the question once to understand what is given in the question. A mercury manometer. Mercury manometer. So here we have seen mercury manometer. Hg is mercury and whose density is 13,550 kg per meter cube. A mercury manometer of density 13,550 kg per meter cube is connected across the length of the pipe to measure the flow rate across the pipe. So in order to measure the flow rate across the pipe, um, as shown in figure 1. So this is the figure 1. So, and we are given the properties of the fluid flowing inside this particular pipe. This is the main pipe. The light color, light pink denotes the main pipe. Dark pink denotes the mercury fluid in the manometer. So let the fluid flowing in the main pipe be of density 2016 kg per meter cube and viscosity 1.57 Newton second per meter square, and it is flowing at an average velocity of 19.3 meter per second. Okay, I hope the question is very clear. So two things in this question. The numbers given are given by myself, so it might not follow the correct physics, but just look at the problem physically and understand how to do the problem, and later apply the concepts in different problems based on Reynolds number or those things, because Reynolds number everything will play a very critical role in the problem solving. For a certain range of Reynolds number, we will be having a certain limits or in certain properties. So all those things take care when you are submitting the assignments. Just see the approach, values and particular formula in the particular regimes like laminar regime, transition regime or turbulent regime. All those things just take care when you are doing the assignment problems. So that is a note I want to make here. So, and coming here, it is question 2. So now we are going to question 2. We will see what is asked in the question 2. What is the nature of the flow? Option A, laminar. Option B, turbulent. Option C, transition. Option D, laminar turning turbulent. Option E, transition turning turbulent. Option F, laminar to transition. Option G, insufficient data. So we are asked to find the nature of the flow. So we are given a certain flow regimes, laminar, turbulent, transition. So what my question here would be, on what basis we are classifying the fluid flow. Like there is one parameter which on which basis we are doing the further calculation. So that is my question. So if anyone would like to answer. Yeah, thank you. We are classifying based on Reynolds number. So here also we are going to do the same thing. So now I mean the answer is transition actually. So here we will see the step by step approach. So what is the formula for Reynolds number? Reynolds number is rho v d by mu. So we need to know what is rho, what is v, what is d, what is mu. So here fluid that is flowing through the main pipe is oil. So oil is, and its density is 2016 kg per meter cube. It is given in the question. And its viscosity is given as 1.57 Newton second by meter square. So and Flow velocity is also given as 19.3 meter per second. Yeah. Flow velocity is 19.3 meter per second. And diameter of the pipe is given as 9 centimeter. So now since all other units are in SI units, we are converting the diameter of the pipe also into 0.09 meter, that is in meters. So now we need to know what is the Reynolds number. So now to find the Reynolds number, we have the formula as Re is equal to rho into V into D by mu. So now we are substituting all the known parameters in the equation. So rho is 2016, V is 19.3 and D is 0.09 meter divided by mu, that is 1.57. I'll just do the calculation once. Okay. 2016 into 19.3 into 0.09 divided by 1.57. Okay, actually it is 2230, not 2228. So since it is above 2000 and below 4000, so we are saying it in the transition regime. If it is below 2000, it will fall in the laminar regime. So based on the Reynolds number, we are just doing the calculation. I mean, we are saying the what regime the flow is happening. Now, after that, we will move to the next problem. Determine the volumetric flow rate through the pipe in meter cube per second. So this is, I mean, all the problems are actually quite simple. In the figure looks complicated, but otherwise the problems in today's class are very simple. So now we are asked to find the volumetric flow rate through the pipe in meter cube per second. So what is the formula for the volumetric flow rate? Volumetric flow rate is given by cross-sectional area into average velocity across the pipe. So that is the volumetric flow rate. How we are getting that formula? Like here it is asked in meter cube per second. So if we think directly itself, it is like meter square is the area and a meter per second is the velocity. So now we are doing exactly the same thing, and Q is equal to A into V. A is the cross-sectional area here and V is the average velocity. So A is a cross-sectional area of the pipe. It is a cylindrical pipe, so it is pi by 4 d square. So it is just a cross-sectional area. So cross-sectional area will be circular cross-sectional area. So it is pi r square or pi by 4 d square. So diameter of the column is again 0.09. So we are calculating the cross-sectional area of the pipe, which is given by 3.14 divided by 0.4 into 0.09 square, which will give us 6.36 into 10 power minus 3 or 0.0064. Yeah. So it is the cross-sectional area is 0.0064 meter square. Now after calculating the area, what we need to calculate? We need to calculate the volumetric flow rate directly, because V is already known. It is given in the question as 19.3 meter per second. So now after that we are substituting Q here. Q is equal to A into V. So here A is 0.0064, V is 19.3. So we are substituting in the original formula and we are just calculating the answer. So it is 0.0064 into 19.3, which will give us 0.1235 meter cube per second. So in case if the question states that volumetric flow rate should be calculated in meter cube per hour, what we will be doing? We will be multiplying by 3600, so that we can get it is that much meter cube per hour. So basically we will be multiplying. So but in question it is meter cube per second, but in one of the practice problems the question is in meter cube per hour. So that is for Q. Now we will move on to question 4. Okay, now in question 4, the pressure drop across the manometer reported in megapascal is dash. So here question is about pressure drop across the manometer reported in megapascal is dash. So here we are not given about the H. In the question, H is actually unknown. If we go and look at the question, this H is unknown actually. We are not given. In the problem statement also, we are not given of the H. If it is given, we can directly say it as rho GH, the difference we can tell. So, but here since it is not given, we are just putting delta P equal to rho Hg minus rho oil, that is mercury minus density of oil into G into H. But here what we know density of mercury as 13,550, density of oil we know as 2016, G we know, but H is unknown. So we cannot go directly with this particular formula. Instead what we can do, delta P we can do. Delta P is equal to, we are just calculating the pressure drop in other ways. So it is F into L into, L by D into rho V square by 2. So here F is a friction factor. So based on the laminar flow or a turbulent flow, it varies actually. So for laminar flow, it is like 64 by Re. But if it is laminar, it is this particular value. But for turbulent, it would be higher. So since we are in the transition regime, we are taking F as 0.035 and we are substituting it in the pressure drop equation, and we are getting the value as this 0.035 into 2.5 divided by 0.0. It will be like some 40 will come. So answer will be like 0.365 megapascal. So now we are going to question 8. In question 8, what is asked is that the expected reading on the manometer reported in meter is dash. The expected reading on the manometer reported in meters is dash. So delta P is actually given as rho into density of mercury minus density of oil into G into H. So in previous problem H was not unknown, so we calculated delta P differently. So now we can use that delta P in this particular equation and back calculate H. So that is how we are going to do. Just a minute. Okay. So we are just taking it and we are just back substituting it. So it is 13,550 minus 2016, that will give us 11,534 into 9.81, it will give us 1,13,148.54 into H. So something wrong. Okay. Sorry. I mean, I just put it in megapascal, so that's why I divided on both sides. But it will be confusing, so we will write it directly in direct Pascal. So it is 113148.54. 48.54. So yeah, so it is. I hope it is clear actually. 365040 divided by 113148.54. So it is 3.2262. So what we are doing basically is we are asked to find the expected reading on the manometer, that is H we are asked to find, and H we are asked to find in meters. So in previous problem itself we have seen the equation for pressure drop as pressure drop is equal to delta difference delta rho or density difference between a mercury and oil into G into H. So it is a density of mercury minus density of oil into 9.81 into H. So when we take this side, we will be getting it as that is 1,13,148 into H, and we have delta P from the previous problem which we have calculated as 3,65,040. So now we are just dividing this value by this value to get the value of H. H is equal to is equal to 365040 divided by 113148.54 equal to 3.23, and H is equal to 3.23 meters. So that is the thing. 5040. Yep. So that is how we got the solution for question 8. Oh, what question 8? Oh, actually, I don't know why it became question 8. It should have been question 5. I'll just change question numbers. It is. So yeah, we have 13 problems, but 6, 7, 8, 4. Now we have the next problem statement. So what is given here? A small ball of diameter d and density rho b falls through a test tube of test liquid having density rho and viscosity mu. It attains a fall velocity v. The fall velocity v can be calculated by the time to fall a measured distance. The formula for calculating the viscosity of the fluid is V is equal to rho b minus rho into g into d square by 18 mu. So if we take mu to the other side, we can get the viscosity. This principle can be used to measure the viscosity of a fluid, and the instrument is known as falling ball viscometer. This result is limited by the requirement that the Reynolds number must be less than 1. Suppose a steel ball of specific gravity 6.59 and diameter 1 mm falls in a SAE 25W oil of specific gravity 0.85 at 20 degrees Celsius. The ball travels a distance of 185 centimeter in 1 minute. So few things. I'll make it small v and it should be alright. So now we will see what is given in the question first. So actually in most of the cases even this experiment can be used for many cases. For example, consider a tall column. Okay, we are allowing a ball to settle from the top to the bottom. So now what we are doing, we are allowing the ball or any small objects, we are putting it from the top and we are allowing it to settle the column. So initially velocity will be there, but after it will be reaching the terminal velocity. So that after that the velocity will remain the constant. It will not be changing with respect to height. So I hope you are clear with the understanding of the problem. So we have one tall column. We are allowing a particle to settle a small ball of diameter d and density rho b. So this ball has diameter d and density rho b, and it falls through a tube of test liquid rho and mu, where it attains the fall velocity v. The v can be calculated. How we can calculate? By taking the distance it covers in a specific amount of time. So since it is a terminal settling velocity, it has reached the terminal settling velocity, so we are allowing it to go through a certain height in particular minute, I mean particular time, and from that we can calculate the velocity. The formula for calculating the viscosity of the fluid is, here it is given, V is equal to rho b minus rho into g into d square by 18 mu. So basically this formula is the formula for the terminal settling velocity of a particle. So V is the terminal settling velocity, rho b is the density of ball, rho is the density of fluid, g is the acceleration due to gravity, d is the particle diameter by 18 mu. Mu is the viscosity of the fluid. So this fall velocity can be calculated by the time to fall a measured distance. So we can calculate v as well. So now from here we are calculating mu. That is the concept in the question. This principle can be used to measure the viscosity of the fluid, and the viscometer is, and the instrument is known as falling ball viscometer. So here everything is known means we can calculate mu. This result is limited by the requirement that the Reynolds number be less than 1. So why does it state so? It means that when Reynolds number is less than 1, the flow regime is Stokes regime. So here viscous force dominates, so we can easily measure the viscosity. But above that it won't be viscous dominated flow, so we cannot use it. So it is limited by the requirement that the Reynolds number be less than 1. So this is the problem statement actually. Now coming to our question, suppose a steel ball whose specific gravity is 6.59 that is its density is 6590 kg per meter cube, and of diameter 1 mm, falls in a oil whose specific gravity is 0.85 or whose diameter is 850 kg per meter cube at 20 degrees Celsius, and the ball here travels a distance of 185 centimeter per minute. So its velocity is 185 centimeter per minute or 185 by 60 centimeter per second. So we can calculate velocity also. So now this is a statement. Based on that, few questions will come now. We have to answer them. So I hope it is clear now. So question 6 is based on this particular problem. What is the viscosity of the oil in kg per meter second? Dash. So as mentioned in the question, these data will help us in understanding the, calculating the viscosity. So in the question it is directly asked what is the viscosity of the fluid, of the oil, that is the fluid in the question. So now we will see how to calculate the viscosity. It is simple. The formula is given. We just need to substitute it back into the formula. So now what we are going to do? We are going to substitute that. Okay. So first let us write what is given. In the ball properties, it is mentioned that ball diameter is 1 mm or it is 0.001 meter, and its density is given. Density is 6590 kg per meter cube, and test liquid properties are also given. Its density is given as 850 kg per meter cube. Its viscosity is unknown, and we are given the speed at which the ball moves. So V is equal to 185 centimeter per minute or 1.85 meters divided by 60 seconds. So it is 1.85 divided by 60, which will give us 0.0308. 1.85 divided by 60, 0.0308 meter per second, and Reynolds number is rho v d by mu, that should be less than 1. That is the condition given in the question. So first let us calculate viscosity mu. So mu here can be calculated as, we'll just substitute mu, everything else, and take mu to the other side. That will give us what is the value of mu. So now we are going to do exactly that to find viscosity of the oil in kg per meter second. So if we know the viscosity of the oil formula, it is mu equal to rho b minus rho into g into d square divided by 18 into v. So we just took mu to the other side and v to this side. We haven't changed anything else. So that is the formula for mu. So now we are substituting all the known things back into the equation. So rho b is equal to 6590 minus 850 into 9.81 into d. D is 0.001 square divided by 18 into v. V here is, we calculated it as 0.0308. So on substituting everything, I'll just recalculate it once again. It is 9.81 into 0.001 square divided by 18 divided by 0.0308. It is 0.1016 kg per meter second. So viscosity, we got it as 0.1016 kg per meter second. So viscosity of the oil we have found out like this. Now we have calculated question 6. Now we will move to question 7. We will see what is asked. This question 7 is also dependent on the problem statement given earlier. What is the Reynolds number? So this question it is about what is the Reynolds number. So Reynolds number, as we all know, it is about Re is equal to rho into V into D by mu. So here we know rho. Rho is the density of fluid. V is the velocity at which it is traveling, d is the diameter of the pipe divided by mu. Mu also we calculated. But here it is not diameter of the pipe, it is diameter of the particle. Why? Because whenever we talk about particle falling, particle settling in a column, we talk about the particle Reynolds number. We don't consider the column or flow Reynolds number. So here our main concern is particle flow, so it is particle Reynolds number. So particle Reynolds number is given by rho v dp by mu. So here dp we use, that is the diameter of the particle. We can make it as well. Here everywhere it is given as d for diameter of the particle. I'll mention it again. So what is the Reynolds number? Rho v d by mu. Here d denotes the diameter of the particle or diameter of the ball. Rho v d by mu. So after that we are substituting everything. Rho is the density of oil. V is the velocity with which the particle is moving in a still liquid, and dp is 0.001 diameter of the particle divided by 0.1016, which we found out. So here it is coming as Reynolds number is equal to 0.2578. So this Reynolds number is less than 1. When it is less than 1, what does it mean? It is satisfying the condition with which the instrument needs to be taken care of. Why? Because if Reynolds number is less than 1, it is the Stokes flow. In Stokes flow regime, viscous forces are dominant. If viscous forces are dominant, this particular instrument can be used for the viscosity measurement. In other cases, it is not possible. So that is the thing. So basically, Reynolds number is the ratio of inertial force to the viscous force. So if it is low, viscous force dominates. If it is high, inertial force dominates. So on that basis we do, if viscous force dominates, we can easily calculate the viscosity, or we can use this particular instrument for the viscosity measurement. So that is the question, and that is the quick answer to this. Now what we will do is, we will calculate question 8. In question 8, what is given is the Reynolds number small enough for a valid estimate. So in this question it is asked that, is the Reynolds number small enough for valid estimate? What does it mean by small enough? It just means it should be less than 1. So our Reynolds number of 0.2578 is less than 1. So it is small enough for a valid estimate. So answer is S. Answer is S. So the Reynolds number is small enough for a valid estimate. So now we'll go to question 9. Okay, these are the unique questions which we saw. Before moving to question 9, we will take a 5 minutes break. I mean, we'll take a 5 minutes. Time now is 4:05. We will start again by 4:10. Sorry, we'll start now. So in the question it is given that consider flow of a liquid of density 890 kg per meter cube and viscosity is 0 kg per meter second through a 9 centimeter diameter pipe as shown in figure. At an average velocity of 4.3 meter per second, a mercury manometer is connected across the length of the pipe. So what is asked in the question is that consider flow of a liquid of density 890 kg per meter cube and its viscosity is 0 kg per meter second. Basically it is an ideal fluid whose viscosity is 0. Through a 9 centimeter pipe as shown in figure at an average velocity of 4.3 meter per second, a mercury manometer whose density of mercury is 13,550 kg per meter cube is connected across the length of the pipe. Determine the volumetric flow rate through the pipe in meter cube per hour. So same problem, we need to calculate the volumetric flow rate. So answer is basically given over here, but yeah, we can still go. So what is given in the problem? First we'll write what is given in the question. Later we will see how to solve the problem. So first thing, it is given that fluid is SAE 30W oil and density of the oil is 890 kg per meter cube. Viscosity is 0. Basically ideal fluid. Diameter of the pipe is 9 centimeter or it is 0.09 meter and average velocity V is equal to 4.3 meter per second. Yeah, 4.3 meter per second. So now we are asked to find the volumetric flow rate in meter cube per hour. So how are we going to do? We have to find the volumetric flow rate in meter cube per hour. So Q is equal to, as we have seen, it is A into V. So A here is the cross-sectional area of the pipe and cross-sectional area is given by pi by 4 d square and V is average velocity, which is 4.3 meter per second. So now we are substituting A in the value of D in the equation for A. So it becomes pi by 4 d square. So pi by 4 into 0.09 square. So that gives us 6.36.00, 6.36 into 10 power minus 3. So basically it is 0.0064 we can keep. Meter square. So we are substituting here 4.3, that is velocity, into 0.0064 equal to it is 0.0274. 0.0274 we can draw. Better to keep 4 digits than going for 5 digits. That's why I am changing. So it is Q is equal to 0.0274 in meter cube per second. So now if we want to convert it into meter cube per hour, what we will do? We will multiply by 3600. It is 98.48 because we changed digits, it became 98.48. But anyways, that is fine. So what does it mean? It just means that if Q is 0.00274 meter cubes in 1 second, in 1 hour. 1 hour has 3600 seconds. So when we are multiplying that particular value by 3600, we will be getting the value as 98.48 meter cube per hour. So that is the thing. Now for question 9, it is question 9. Now we will go to question 10. Okay. In question 10, what is given? A simple falling ball viscometer can be used to measure the viscosity of simple fluids. A small ball of diameter d and density rho b falls through a tube of test liquid whose density is rho and viscosity is mu. Fall velocity v is calculated by the time to fall a measured distance. The formula for calculating the viscosity is V is equal to rho b minus rho into G into d square by 18 mu. This result is limited by the requirement that the Reynolds number rho v d by mu be less than 1. I think I should change it before also. Okay. Rho v d by mu is will be less than 1. Suppose a steel ball of specific gravity 7.87 of diameter 2.2 mm falls in SAE 25W oil of specific gravity 0.88 at 20 degrees Celsius. The measured fall velocity is 8.4 centimeter per second. What is the viscosity of the oil in kg per meter second? So actually I have one problem which is 13th problem, that is the last problem, in which there is a different variation to this particular question. But this particular question is similar to the one we saw in the last slide only, but that question 13 is different. So now we will just see the simple solving approach which we used in the last problem as well. A simple falling ball viscometer, that is we are allowing a ball to settle or a smaller particle to settle from a certain height inside a tall column, and we are measuring the distance which it covers in a certain period of time, that will give us a velocity. So by using the velocity, what we can calculate is that we can calculate its viscosity. So it is a viscometer. Normally what are all the approaches we use to calculate viscosity? We use rheometer, like a parallel plate, uh, and what do we call, cylinder, I mean two cylinder, I mean the fluid will be between two concentric cylinders, or it will be between two parallel plates, and we will be applying the shear, or it can also be like a cone will be there, cone and cylinder. So all types of viscometers are there, but for one of the those are all complex, but here it is a simple approach wherein we are just allowing a ball to fall through a liquid. So it is a simple falling ball viscometer, and the ball diameter is d and its density is rho b, and it is falling through the test liquid, and the liquid density and viscosity is rho and mu. So the velocity, normally this formula we use it to calculate the terminal settling velocity of a particle. But here, since it is known, we are using it to find the mu. So that is the difference. But here there is one major limitation, that Reynolds number should be less than 1. Why? Because it is only below less than 1, we will have viscous forces to be dominant. In all other regions, viscous force might not be dominant. Suppose a steel ball whose diameter is 2.2 mm and density is 7870 kg per meter cube, is falling in a oil, and oil properties, that is in terms of specific gravity, is given. We need to find the viscosity first. Fall velocity is 8.4 centimeter per second. Now measuring viscosity is very straightforward approach here. We are just going to use this particular formula. So what is the viscosity? So ball properties, first we will write, I'll just make sure it is right, because since values are changed it might be different. 7870 880, 7870 and 880, 2.2 mm and 8.4 centimeter per second. Okay, so all the values are right actually. So diameter is 2.2 mm or 0.0022 mm, sorry 0.0022 meter. Density rho b is given by 7870 kg per meter cube, and test liquid properties are given as density is equal to 880 kg per meter cube, viscosity is mu, and V we know it as 8.4 centimeter per second, it is given in the question, or it is 0.084 meters per second. So now Reynolds number should be less than 1, that is the criteria which it should satisfy. To find, we need to find the viscosity of the oil in kg per meter second. So we are just going to use the same formula and we are going to calculate the value. Mu is equal to 7870 minus 880, that is density of oil, and sorry 880 into G 9.81 into D, that is diameter of the particle 0.0022 whole square, divided by 8 divided by V, that is 0.084 meter per second. So that will give us 0.2195. Viscosity is given as 0.2195 kg per meter second. So the normal viscosity of oil is 0.001 kg per meter second. So when compared to the viscosity of water, we can find the viscosity of oil as 0.2195 kg per meter second. It is almost 100 or 200 times, almost 200 times higher than the viscosity of oil. So you can imagine how this particular things can be used to measure the viscosity of the oil, because if viscosity is low, again the Reynolds number will become high. So all those things are there. So Reynolds number becomes high, inertial forces will be dominant. So we need to be cautious of using all those factors. Only since viscosity is high, we are getting the we can use this particular setup for measurement of viscosity. So that is the conclusion. So normally we can see, right, in our homes itself, oil will be thinner and its viscosity will be low, or similarly, but compared to it, not oil, water viscosity will be low, it will be very thin, right, compared to oil. Cooking oil or any oil, if we take, its viscosity will be high compared to water, right? So it will be thicker than water. So those are all the things which plays a role. So that's it actually. So mu is 0.2195 kg per meter second. So now we are substituting these things back in the equation. What is, we found out the mu. So question 10 was about finding mu. In question 11, what is the Reynolds number? Question 11 is all about finding the Reynolds number. So how will we calculate Reynolds number? Again, it is a simple formula which we have been using for a long time. Re is equal to rho v d by mu. So since it is a particle's Reynolds number, we will be using rho v dp by mu. So rho is 880, v is 8.4 centimeter per second, so it is 0.084 into dp is 0.0022, 2.2 mm. divided by mu, which we found out as 0.2195. So that will give us Reynolds number as 0.74. So this Reynolds number is comparatively higher than the Reynolds number which we saw in the previous problem. There it was 0.25, here it is 0.74. It is almost high. The reason is that particle is uh, quite um, larger, and there it was only 1 mm, here it is 2 mm, and velocity is also high here. There it was 195 something centimeter in a minute. So it was okay 195. Yeah, it was only 3 point. I mean, if we calculate it is 3.25 centimeter per second. Here it is high. So when velocity will be high, when viscosity will be comparatively lower, it is 0.2195. I think there it would be comparatively, it should be higher. We'll just compare it once. Okay, and here it is not high, but since all other factors were playing a role, density is also low. But how it is then? I mean, diameter of the particle played a role, so that's why the difference. So anyways, but Reynolds number here is comparatively higher than previous problem. Okay, so what is the Reynolds number? We are calculating the Reynolds number. So now what uh, question 12 is about, is the Reynolds number small enough for a valid estimate? So the question is asking, is the Reynolds number small enough for a valid estimate? So since it is less than 1, we can say that yeah, it is small enough for the valid estimate. So the Reynolds number is satisfying our required condition. It should be less than 1. If since it is less than 1, this particular setup can be used for measuring the viscosity, uh, and it can be used as a simple simple falling viscometer. They gave some falling ball viscometer. So yeah, it can be used. So is the Reynolds number small enough for a valid estimate? So is it, I mean, the question basically means, is it small enough for measuring the viscosity? So yeah, answer is yes. Since it is lower than 1, lesser than 1, it can be used. It is small enough for a valid estimate. So coming to our last question for today's session. So as I mentioned, this question is conceptually similar to the previous problem, but here we have one major difference which we will see in the towards the end of the problem. So but problem is similar, concept is similar, everything is similar. So we will ask the question. Okay. A small ball of diameter d and density rho b, when falls through a tube of test liquid rho and mu, it attains a fall velocity v. The fall velocity v can be calculated by the time to fall a measured distance. The formula for calculating the viscosity of the fluid is dash, is given by v is equal to rho b minus rho into g into d square by 18 mu. This principle can be used to measure the viscosity of a fluid, and the instrument is known as falling ball viscometer. This result is limited by the requirement that the Reynolds number be less than 1. Suppose a steel ball of specific gravity 2.87 of diameter 1 mm falls in a SAE 25W oil of specific gravity 0.85 at 20 degrees Celsius. The ball travels at a speed of 10 centimeter per second. Is the Reynolds number small enough for a valid estimate? Actually, two things: the oil name and specific gravity. If it doesn't match, don't ask me, because values I have changed. Oil name also, like, it should have been removed in the previous problem itself. I'll remove this better because it would be like misleading sometime. I think I should remove everywhere, I guess. How did it come here? I don't know why I mentioned the oil name here, but anyways. Yeah, don't see oil name and its properties. It might not match actually. Yes, here we haven't given. So anyways, we can. So what we are going to do, we are just going to substitute everything. First, the ball properties. Ball diameter is it 2.2 mm? It is 1 mm actually. Why did I mention 2.2 mm? Okay, I mentioned everywhere as 2.2 mm, so we will better change it in the question as 2.2 mm. That would be better actually. Again, these velocities, everything should be italicized. Where is it? It is of diameter 2.2 mm falls in a oil of specific gravity. Okay, 2.2 mm. Density is 880 kg per meter cube. Again, I didn't change density here. 8 uh 2870. What did I? 2.87. 0.1 centimeter, 10 centimeter per second. Yeah, everything else is same. So what is given? Ball properties. The diameter of the ball is 2.2 mm, so it is 0.0022 meter, and density of the ball is 2870 kg per meter cube. And liquid properties is it is oil and whose density is 880 kg per meter cube and viscosity is mu. And velocity is given as 10 centimeter per second, or it is 0.1 meter per second. And Reynolds number should be less than 1 for it to be used as viscometer. So if we go back and look at the question, what is given is that what was asked to find, what was asked in the question is that it is given falling ball viscometer principle is given, which we have already seen in the last couple of problems. I mean similar problems we have seen in today's session itself. So this result is limited by the requirement that the Reynolds number be less than 1. Suppose a steel ball of diameter 2.2 mm falls in oil at a 20 degrees Celsius whose specific gravity is 0.88 and steel ball specific gravity is 2.87, and the ball is traveling at a speed of 10 centimeter per second. So is the Reynolds number small enough for the valid estimate? So we should calculate whether the Reynolds number is small enough for the valid estimate. So based on that, what we are doing is that we are taking it V is equal to 10 centimeter per second, and Reynolds number is rho V d by mu, which is less than 1. I mean it should be less than 1, and we should I mean we need not find actually. First let us find is equal to mu is equal to viscosity of the oil in kg per meter second. So we are substituting all the known values in this particular equation. So mu is equal to rho b, that is 2870 minus 880 into 9.81 into 0.0022 divided by 18 into 0.1. So what does this give us? We are getting the viscosity as, I just recalculated once just to make sure there are no any calculation errors. So 9.81 into 0.0022 square divided by 80 divided by 0.1. So it is 0.0525 kg per meter second. So that is the viscosity of the oil. So but now in the question it is not asked to find the viscosity of the oil, rather it was asked to find the whether it is a suitable thing, whether the Reynolds number is small enough. So first, for that we need to find um, the Reynolds number. What is the Reynolds number? The Reynolds number is given by Re is equal to rho V d by mu. So here rho is 880, V is 10 centimeter per second, and d, that is diameter of the particle, is 0.0022, and mu is 0.0525. 880, 0.0525. So that gives us Reynolds number as 3.6876 or 3.69. So now if we look at Reynolds number, what are we able to see? We can see that Reynolds number is higher than 1. Its value is greater than 1. So this particular viscometer or this particular setup cannot be used for the viscosity measurement, because at this stage it is like it is like higher than 1, so it is not under Stokes regime and viscous forces are not dominant anymore. So I mean, it is not a turbulent regime as well, but it is in the transition regime, so it is better not to use this particular type of viscometer. So answer is the Reynolds number small enough for a valid estimate? So that was what asked in the question actually. If we go back and look at the question, the principle can be used to measure the viscosity of the fluid, and the instrument is known as falling ball viscometer. This result is limited by the requirement that Reynolds number be less than 1. Suppose a steel ball is falling through of this particular diameter is falling at 20 degrees Celsius. The ball travels at a speed of this particular, is the Reynolds number small enough for a valid estimate? But since our Reynolds number is greater than 1, we cannot say this Reynolds number is valid for this particular estimate. Rather, answer is actually no. Since Reynolds number is greater than 1, the Reynolds number is not small enough for a valid estimate. So we cannot use this particular combination of fluid and the particle for measuring the density. So what can be done here is that to measure the density, to measure the viscosity of the fluid, what we can do is, one thing we can do is if it is actually if the velocity is low, in place of 10 centimeter per second, let us consider it as 0.05. So at that time what it becomes is that 880, okay, 880 1 into 0.0022 square divided by 80, so divided by 0.05, it will be 0.105. I mean, even then it will be high, but if it is instead of 0.5 centimeter, if it is 2 centimeter, what will happen? It will be 0.02. We will have 0.2625 kg per meter second as viscosity. At that point, what will happen? 880 divided by this into 0.1. Okay, here it becomes it won't be 0.1, right? It will be 0.025 and it will be 0.0022. It will be 0.18 if velocity is 0.025. If velocity is 0.05, what happens is 3.69 divided by 4. Even then it would be 0.92. So but it is less than 1. So when velocity is half or less than half, in this particular condition, we can use this particular setup to measure the viscosity of the fluid. So we should choose the particle properties in such a way that we will be getting that low velocity, so we can fine tune the density of the ball, or density and diameter of the ball. So we can tune that and we can get the velocity in that particular region. So if that is the case, we can use it for measuring the viscosity of the fluid. So this is how we can change it for different conditions. So yeah, that is how we can do it. If but for this particular condition given in the questions, it is not suitable. That is our conclusion right now. So answer is no. So yeah, thank you for today's sessions. If you have any doubts, you can ask, and these PPT and videos which are recorded will be given to you, so you can use those for submitting while submitting assignments. Yeah. Again, we will have next week a class from 3 to 5 p.m. If there are any changes in the timing, it will be informed to you through NPTEL before some time. So yeah, I mean, that's all from my side. If you have any doubts, you can ask me. Okay. Thank you so much for attending today's session. Since I guess that's it, right? I hope it is done. We'll meet again next week. Mm. So yeah, thank you. We'll meet next week. I don't think I have any more announcements. If there are any changes in the presentation or any changes in the video, I'll notify you prior only, so we can follow that. Okay. Well, yeah. I guess that's it. I I'll close the session. Thank you.